In this video, I'm going to go through the third review for Corollary 3, just in case you finished it and you wanted some extra practice and you need some explanation on these answers. So for number 1, in the diagram of triangle ABC, points D and E are on AB and CB, respectively, such that AC is parallel to DE. So essentially, they're telling us that these triangles are similar by a corresponding angles argument. If AD is 24, DB is 12, DE is 4. What is the length of AC? Well, when I have these triangles overlapping, I always think it's a good idea to separate them. So my big triangle, ABC, this is not going to be drawn to scale, but you get the idea, has a length for AB that's 24 plus 12, so that's 36. And I'm looking for AC, which is X. And for my smaller triangle, triangle EDB over there, I've got a side length of 4 and a side length of 12. So if I set up a ratio of corresponding sides, I can set my big side X. That should correspond to that 4 DE equals the 36 over the 12. So big over small equals big over small. When I cross multiply here, X times 12 is 12X, and 36 times 4 is 144. When I divide out to 12, I get X equals 12 as my missing length for AC. So just be careful. I didn't actually use that 24 anywhere in my proportion here, because that's not a side length of a triangle. The only reason I have that is to help me get that 36 there. So it might be a good idea to redraw these triangles to help give you an idea. Number 2. In the diagram of the right triangle ABC shown below, AB equals 14, AC equals 9. What is the measure of A to the nearest degree? Well, if I'm looking for an angle and I'm given some sides, I know this is going to be a right triangle trigonometry problem. So I'm going to write down SOHCAHTOA just to help myself out there. And from angle A, I notice I have the adjacent side that's right next to it, and I know the hypotenuse that's opposite the right angle. I don't know what the opposite side from angle A is, so I'm not even going to mention it. And the ratio that relates the adjacent to the hypotenuse is cosine. So really, the cosine of angle A is equal to my adjacent side 9 divided by my hypotenuse 14. And if I'm searching for an angle, I'm going to use inverse trig on my ratio of sides. So when I type that into my calculator, second cosine gives me inverse cosine. You get about 50 degrees, 49.99. So that's the measure of angle A there. Number 3. Segment MN has endpoints M at -6, -3, and N at 9, 7. And I want to find a point Q on it such that it breaks it into a ratio of 3 to 2. Remember, that's 5 parts total. So the first thing I'm going to do is I'm going to take my straight edge, and I'm actually going to make a right triangle out of this, because it's kind of hard to break up a diagonal segment, but a horizontal piece or a vertical piece is going to be a lot easier to deal with. So what I'm going to do is I'm going to look at this distance on the horizontal. Looks like that distance is 15 boxes altogether. So if I want to break that into 5 equal pieces, I'm going to make a tick mark every 3 boxes. And if I want it to be a 3 to 2 ratio, I'm going to go to the third one in, then just draw a vertical segment up to my line segment, and it looks like Q is going to be at 3, 3. So I don't work with the diagonal. It's easiest just to segment that horizontal piece to make my partition. For number 4, in the diagram shown, altitude AC is shown to form a right angle with BD. It gives me the length of CB, 16. I know the length of AC, I believe on your papers it's 10. And I want to find the length of DC. So this is a right triangle with an altitude dropped. So it's either going to be a Hills or a SAS problem. And the question you need to ask yourself is, do I know what the altitude is, or do I care about the altitude? Yes, it's 10 right there. So this has to be a SAS problem, not a Hills problem. So I'm going to label one of those pieces as side 1, and I'm going to label the other piece as side 2. So I'm going to take side 1 over my altitude, 10, equals my altitude 10 over side 2, 16. To solve any good proportion, I'm going to cross multiply. 10 times 10 is 100. X times 16 is 16x. And when I divide out my 16, I find that my missing piece DC is just 6.25. Number 5. To find the distance across the pond from point B to C, a surveyor drew the diagram below. The measurements he made are indicated on his diagram. Use the surveyor's information to determine and state the distance from point B to point C to the nearest yard. So I'm looking for this piece right here. Again, this looks like a similar triangle's proportion, where I could do big over small equals big over small, but you need to recognize this 85 is not the side length of a triangle. For the big triangle ABC, that's going to be 230 plus 85, or 315 yards as that big piece. So what I could do is I could take 315, that corresponds to the small side of triangle ADE, AE right there, 230, is equal to the big side I'm looking for is BC, which I've labeled as X, and its corresponding small side that's proportioned in the same way is going to be DE, which is 120. Again, I'm going to cross multiply. 230 times x is just 230x. And 315 times 120, if you type that into your calculator, you should get 37,800. I'm going to divide out the 230. And it tells me to round to the nearest yard, so I shouldn't have any decimal places. So it's about 164 yards when I plug that into my calculator. So be careful not to use the 85 anywhere in your proportion, again, because that's not a side length of a triangle. Number 6. A man was parasailing above a lake at an angle of elevation of 32 degrees from a boat. If 129.5 meters of cable connected the boat to the parasail, that's that hypotenuse right there, how many meters above the lake was the man? So I'm looking for that side of the triangle right there. Well, if I'm missing a side and I'm given an angle, this is probably a right triangle trig problem. So again, I'm going to write down SOHCAHTOA just to help myself out. And I notice that I have the hypotenuse, and I'm looking for the opposite side from my angle. The ratio that relates opposite to hypotenuse is going to be my sine ratio. So I'm going to take sine of my angle 32 degrees, that's the angle I'm looking at, equals my opposite side, which I'm looking for, that's x, divided by 129.5. Again, when you do this, remember your calculator needs to be in degree mode anytime you're doing trig. So this is just a proportion. Makes it more obvious how to solve it if I put sine of 32 over 1. So I'm going to cross multiply. X times 1 is just x. And when I multiply 129.5 times sine of 32 in my calculator, it says to the nearest tenth of a meter. You could type it in just like this. Should get about 68.6 meters. So the tenth is just one decimal place. For number 7, rectangle ABCD is shown with diagonal AC drawn. Point F is on AC and point E is on DC such that FE is perpendicular to DC. So there's a lot we need to take in here. I want to prove the triangle ABC, this top triangle, is similar to triangle FEC, that one down there. Anytime I'm trying to prove two triangles are similar, it's always an angle-angle argument. So I'm going to write down two things in my givens. They're telling me it's a special quadrilateral for a reason, so I want to think about my properties of a rectangle. And they told me that FE and DC were perpendicular. Let's try to think about what perpendicular lines do. They form right angles. So I know that angle FEC right there is a right angle, but I also know that angle B is a right angle because that's a property of a rectangle. The rectangle has four congruent right angles. So there's a lot you could do here to separate this. You could say that that's a right angle, that's a right angle, then state that they're congruent. Or, if you want to jumble it all into one statement, it would look something like this. So I could say the triangle FEC, don't call it angle E because there's two different angles at E, is congruent to angle B. Now there's only one angle at B, so I can call that B. And my reason is twofold. It's that perpendicular lines form congruent right angles, and rectangles have 4 right angles. So in terms of my angle-angle argument, I'm already halfway there. Now, I need to think of what's another property of a rectangle that might help me get another angle. And it's always a good idea to look for parallel lines. And I notice that AB and DC should be parallel because that's a property of rectangles. And if I can make that argument, I could try an alternate interior angles argument at A and C. So what I'm going to start with is, because I need those lines to be parallel before I can say alternate interior angles, I'm going to state that AB is parallel to DC, because in a rectangle, opposite sides are parallel. Now that I've mentioned that they're parallel, I'm going to mark that angle up there as angle 1, and that angle down there as angle 2. I'm going to make an argument to say that angle 1 is congruent to angle 2, because parallel lines form congruent alternate interior angles. Again, if I'm proving triangles are similar, that's all I need. I've got an angle right here, and I've got an angle right here. So my last step in my proof is always exactly what they're asking me to prove. Triangle ABC is similar to triangle CEF by angle, angle.